I'm excited to present AuthentiSense. It's a result of joint collaboration among Technical University of Darmstadt, University of Würzburg, and company Kobil. So together we worked on how to design kind of scalable behavior biometric authentication system that enables continuous authentication using few-shot learning concepts for mobile platform. So today I'm thrilled to share our findings with you guys. So basically, mobile applications are widely used in online services, and the trend is amplified by corona pandemic and forced many business or traditional business to move online services. So these mobile applications handle a lot of data, most of them sensitive and kind of critical data. So that data should be protected. So it calls for kind of authentication process to secure the data against kind of digital threats. Unfortunately, traditional authentication systems suffer from some limitations. For example, multi-factor methods, basically they are vulnerable to phishing attack or session hijacking attacks. And also they are not very convenient in terms of user perspective. And similarly, one-time method like passwords or physiological biometrics also have their own limitation. For example, password can be forgotten. And if these biometrics are exposed, then they can be multiple times reused by the attackers. So it calls for further development and research in these areas. So several kind of authentication mechanisms have been proposed, including behavioral authentication. Basically, it monitors in kind of frequently and non-obtrusively monitors user interaction with the device and tries to identify kind of unique individual regularities from user behaviors. And by analyzing several patterns like motion patterns, typing, etc., then can comprehensively profile user behavior that can kind of add an extra layer of security to the authentication process. Despite their benefits, they face some challenges. So basically, they need large amount of training data if you want to have a kind of accurate model. Also, they are not scalable because they work for a limited amount of user they initially were trained for. And also, in order to have a kind of performance model, you need to have a model per user, which impacts the usability. And also, they require long interaction with the device that has its own disadvantages. So it means we have to also design kind of system that overcome these challenges and limitations. So to do so, we designed AuthentiSense. So our main contribution. So first of all, our system is fast, efficient, because we do not require handcrafted features. And since we do not do feature engineering manually, so yeah, it's fast. Our experiments also approve that. It is scalable, can authenticate millions of users because we use concept of few-shot learning. We use kind of architecture. It's called Siamese neural network. So if trained on a representative sample of users with enough diversity, then can be used for authenticate many users. And last not least, so our model is user-agnostic. So it means we don't need to retrain the model when user population changes dynamically, when user leaves or join. So before move on to technical details, I would like to give you some background about few-shot learning compared to a standard supervised learning algorithm. So let's consider classification, image classification. So the architecture to go is CNN, convolutional neural network. So basically it involves feeding a lot of data, which is annotated, labeled data to the model. So the data passes through layers of kind of transformation operation like pooling layer, convolutions, and then features are extracted and are fed to a fully connected layer, and then prediction is done. So one of the known problem of this kind of architecture is that when you face out of distribution data, because this model can learn from the training data and generalize to somehow similar similar data that has kind of similar distribution to the training set. So in contrast, few-shot learning is an approach in machine learning that replicates how human learns by generalizing knowledge from a few examples of the data. So unlike standard supervised learning, it does not learn exactly like them from training data. So they identify or they train kind of similarity function. They try to identify similarity or dissimilarity from the inputs. And I will explain this architecture later when I just talk about the AuthentiSense. So to train our model, we use a data set that contains 45 users. So basically to make sure our model is generalized and is effective, so we split data set to 3 subsets. So 35 user for training, 7 for testing, and 3 for validation. This is kind of a normal and standard approach in any machine learning projects. So each user in data set has 15 sessions lasting 90 seconds. So basically, our focus was on real deployment of AuthentiSense in the mobile banking application. So the data actually was captured from real-world users working with kind of real-world mobile application. And also it contains users with different genders, professions, and also ages to ensure it covers a wide range of the behaviors. Also, it includes frequently used function in mobile banking application, 5 transactions, payment, credit card balance, etc., and also 3 posture, sitting, having phone in hand, and etc. So also the data captured through 3 sensors, so namely accelerometer, gyroscope, and magnetometer. So accelerometer basically measures the phone acceleration, which is used to capture motion patterns like tilting or shaking. Gyroscope is used to measures basically angular velocity, which is used to capture kind of rotational movement like rotating and flipping. And magnetometer measures the magnetic field of the phone, which is used to capture directional changes, rotating from landscape to portrait. So I will explain in the following the main components of the system and their specific functionality very briefly due to time limit. So basically, the first component is Siamese neural network, which is to function like a feature extractor. So basically, it contains 2 identical subnetworks or sister networks with the same architecture that share weights. So basically, they learn embedding, which is meaningful representation of the input behavior. And then it follows by a distance function. Sometimes they are called energy function. So basically, it calculates a distance, can be any distance, for example, cosine or Euclidean distance from the output embedding, and then gives you a distance. So basically, it regulates small and large distances. And after that, decision network comes, which is kind of classifier. So basically, it's fully connected neural networks trained using binary cross entropy loss function. And if the distances among the embeddings are, to somehow they are close, it outputs 1, otherwise 0. So to train the network, basically training pretty much depends on the sample generation strategy. And there are 2 main sample generation, pairwise and triplet. So in pairwise, basically we make a pair of inputs. If they are similar, we call it positive, otherwise negative. But in triplets-based sample generation, we have 3 samples. So we have anchor, we have positive, which is another variant of anchor. For example, they belong to the same user or same class, and negative, which is different than anchor. So basically, for each kind of this sample generation strategy, network should be trained by different objective function. For example, for pairwise, we can use contrastive loss function or binary cross entropy. and for triplet, we use a triplet loss function. But triplet loss function is more effective in learning to discriminate similar or dissimilar samples. It considers the relationship between a sample and another set of samples. So for this, we just selected triplet loss for training our network. So basically having the triplets, we feed it to the network. So we calculate the embeddings for anchor, positive and negative. So the objective is, okay, we have to minimize the distance between positive and anchor and maximize the distance between the negative and anchor. So if simply we use this loss function, so neural network, this encourages neural network to converge to the kind of trivial solution. For example, all the input, all the embeddings if are zero, so the network does not learn anything. To avoid this, we add hyperparameter alpha, which can be the kind of control the hardness of triplet. I will explain later what are the different type of triplets. Then if we put it in a loss function like that and train the network, then we see this loss function encourages model to map the similar samples close together and map this similar sample farther apart. And you will see at the end, we have kind of a nice cluster of embeddings for each users that they are well separated and can be used for authentication process. So depending on location of the embedding, the negative to the relative to the anchor and positive, we will have three triplets. Not all of them provide equal utility for optimization. Optimization through the loss they provide. So the first one is the negative. If you plug it in the loss function, so the loss is zero, then does not provide any useful information for the training. The hard one, you see, they are very close to the anchor compared to the positive, but they provide positive loss. And the problem is that they collapse the training process, and optimization process will get us stuck in the minimum, local minimum, and loss does not increase. So but the better solution is semi-hard triplet. Basically, it's kind of trade-off between them. The loss will be positive and also provide useful information. So after training the Siamese neural network or feature extractor, then we have to train the decision network. So to do so, we train the Siamese neural network with triplet loss function. Then the weights are frozen, and then we append decision network to the network, to the system, and then using binary cross entropy loss function, we just do the optimization and optimize the weights ready for the authentication process. So to evaluate our system, basically, we have used several mostly used metrics in context of biometric authentication, false acceptance rates, false rejection rates. So these are two types of error. Our objective is to minimize these two errors. And basically, we have to calculate the point at which these two errors are kind of equal. So it is equal error rates. So we calculate equal error rate using validation data sets, and then we have this threshold. When we apply it to the system, we put it in decision network thresholds, and then calculate it for unseen test, and we just got pretty decent equal error rates or false acceptance and false rejection rate compared to literature. So we only we didn't rely only on FAR and FRR. We also considered F1 score, which is kind of balanced between precision and recall, because it gives you a comprehensive picture of the system in terms of performance, and also will help you to make informed decision when you want to deploy the system. So basically, we conduct kind of extensive experiments using different loss functions, and also using different variables like authentication window time and nshot, which is a number of enrollment sample to compare with the test or query. So basically, for all of these variables, triplet loss function outperformed contrastive loss function and binary cross entropy. We got a 97% accuracy in terms of F1 just with 3 shots in 1 second user interaction, and even we were able to get 95% with one shot or comparing with one enrollment sample. So This brings me to the end of presentation. Just I summarize the contribution and I will present some key performance numbers. So basically, our system is efficient and does not require handcrafted features. So it's scalable, can authenticate millions of users, is user-agnostic. You don't need to retrain model, and then can achieve pretty decent performance in terms of one score, RR and FAR. And last not least, so basically we can authenticate the user only 1 second after 1 second user interaction. So I hope this work has provided valuable insight into the potential application of motion-based behavioral user authentication. I'm happy to take any question.
At the beginning, you mentioned one of the disadvantages of existing biometric authentication is the cancelability issue. For example, if your fingerprint is stolen, you cannot reset it. It's stolen forever. But in this work, I think you use the motion recognition, which is also a kind of biometric approach. So I'm wondering, so say if the attacker has somehow got your motion signal from the user and identify some unique features of this user, then how is the proposed algorithm to defend in this scenario?
Good question. So basically, according to our threat model in the paper, so one of the point that attacker can attack our system is just through injection kind of data to the system. So before going to this section, I have to tell that basically compared to the photos or fingerprint, constructing motion-based behavior is very challenging. It's not easy. So that's why it adds another layer of security. And if attacker can do that, so to us, attacker is kind of Turing machine, can do anything. Nobody can say, okay, this is our limitation of the attacker because we have no idea of attacker capability. And basically, first of all, it is very hard and difficult and challenging for the attacker to do so. And if he wants to do something like that, so he has to kind of inject kind of spoofed motion sensor behavior to the system. But we have other assumption. For example, these sensors can be protected by hardware security technologies like ARM Trust Zone. You can just assign the sensors to this enclave, and then it's not accessible even to the OS in case of OS is compromised. So basically, it's very hard and challenging. I'm not going to say it's impossible, but it's very hard and challenging. And we know that. So basically, there is no 100% security. If you want to make something 100% secure, then you have to buy a safe, put your system in it and lock it. But also you have to be kind of, you have to have hopes and dreams. There is no earthquake, flood, something like this.